ways of coping with NP-complete problems. And two common techniques are backtracking, intelligent backtracking, and branch and bound. Backtracking is appropriate when you are doing a search problem. You just need a solution. So you try to go toward a solution. Sometimes you have to back up and try again, and you eventually reach the solution and you're done. Branch and bound is appropriate when you got to find, for an optimization problem, where even when you find a solution, you still got to back up and try again to see if you can find a better solution. So I'm going to start today by showing, first I'm going to show you some code examples of this stuff in action, and then we'll move to talking about the abstract. Okay, so this is a C# implementation of a 3-sat solver. So let me start by running it. Make sure I got everything initialized the way I want. Do something small like 5 variables. So what this does is it creates a random formula. So what I've told it to do is to use 5 variables. So it'll create 5 different variables. And then it will create 15 clauses. So let me run it and I'll talk about what I mean by clause. So,
15 mass terms?
So you can see up there that the 5 variables are x0 through x4. And remember, when you're in 3-sat form, it's the conjunction of these disjunctions. The disjunctions are the clauses. So the first clause is not x3 or x2 or x4. And the next clause is x1 or x3 or not x0. And those are all ANDed together. So that's 3-sat form. You can take any formula, of Boolean logic, and put it into that form. And so then what it does is it takes those 5 variables and it generates, in this case, I think it's 25 clauses to make a formula. And then it goes about trying to solve it. And you can see that it gave the solution there, that x0 should be true, x1 should be false, the other should be true. And it tells you that there's a recursive method that we'll look at. And it's telling us that that recursive method was called 9 times in the process of solving this thing. Okay? So we don't always get so lucky. Okay, well, that was not, oh, it's the same problem every time unless I change the seed. Okay? So let's do that. Let's change the seed. So we'll make the seed be 8. And I'll run it. And that time it took 13 calls to solve. Now, that's a pretty small problem, and we can increase the number of variables. So let's increase the number of variables to 25. What the heck? Okay, so now 25 variables, and so it gives 5 times as many clauses, so it would be 125 clauses. Okay, so that time it did 39, 90 calls and found no solution. So we're handling 25 variables okay. So let's try 40. Okay, so there's our clause. And you can see it's counting up the number of calls. So we seem to have come to a problem that's kind of big for it to solve.
And this is with backtracking?
Yeah. So it went almost 700,000 calls before it could discover there was no solution. Now, we had a talk here, I don't know if it was last year or the year before, by a researcher who had won the Turing Award. And one thing he talked about was research into solving this problem. It turns out that it's a problem that needs to be solved if you're doing program verification or hardware verification. Essentially, you can describe conditions that have to be true about the program in terms of predicate logic, and then you got to try to solve it, and you need a 3-sat solver. And he was saying that industrial strength 3-sat solvers could solve expressions like this that contained millions of variables, like a million variables. If the example was a practical example, if it was an example that actually arose out of a need that was created to prove something, but that formula is generated at random, the solver couldn't go above a couple hundred variables. Okay? Or maybe it's a couple thousand. Anyway, it was a whole lot less. And so he was just talking about the difference between, that often comes up, that you can come up with an algorithm that will solve these NP-complete problems pretty well if the problems arise in practice, but not so well if they're generated at random. And he felt that further research was needed to understand the difference between problems that arise in practice and problems that are generated at random. Yeah?
So does that mean what comes up in practice is not random?
Well, surely, yeah, what comes up in practice is not random, but what is it about the ones that come up in practice that makes them apparently easier? And he didn't know, he was just raising that as a research area. Okay, so we're right at the threshold of what this solver can do. Let me show you how it works, and we can see how to improve it. Okay, so the main method just generates the random formula, and I'm not going to go into the representation. I'm not really satisfied with this program. But, I mean, there are a lot of classes because you got a formula, and the formula contains clauses, and clauses contain variables, and there's a lot of code to represent things. But the fundamental solver is actually pretty simple. So one thing I do to try to speed things up is, rather than pass a lot of parameters, I just have some static variables. So I use global variables to avoid the overhead of parameter passing. Because if you're doing hundreds of thousands of these method calls, the cost of passing parameters can add up. So calls is just a number that tells you how many times a method's been called. That's what I'm displaying. Formula is the formula we're trying to satisfy. Now the formula contains variables. Some of them I call unbound variables, and some I call bound variables. So the unbound ones are the ones that we haven't, initially all the variables are unbound. We haven't committed to whether they're true or false. At some point, we'll pick a variable and say, let's assume this variable is true. At that point, it becomes a bound variable. So all the variables that are currently unbound are in the unbound set. All the ones that do have a value are in the bound set. And so to set things up, I create an unbound variable set that contains all the variables. I create a bound variable set that's empty. I set the formula, and if I set calls to 0. And that's in my constructor. And then I have the solve method that I call. So this is, of all the code, this is what illustrates backtracking. So let's look at how it works. We start by incrementing the call count. Then we check to see if the formula is empty. So there's going to be a base case in backtracking. And in this situation, the base case is when the formula is empty. So the way a formula becomes empty is as we proceed through the search, we're going to, like I said, make assumptions about variables. So we're going to do something like, let's assume x0 is true. Then we're going to look at the formula. If that assumption makes any of the clauses false, then we fail right then and there. Right? That assumption has led to a dead end, because you've got to make all the clauses true. If it makes some of the clauses true, but not all of them, well, if it makes some of the clauses true, we pull them out of the formula, remove them from the formula, making the formula simpler, which means that over time the formula gets shorter and shorter as we remove the true clauses, and eventually it becomes empty. So when it becomes empty, that's when we have succeeded. We're trying to remove all the true clauses we're trying to move all the clauses because they're true without ever having to get stuck because one is false. So there's our base case. So this solve returns true if you found a solution and false otherwise. Right, now this is where we decide, this is where we pick a variable and start making an assumption about it. So I've got two ways of making a choice, and right now all I'm doing is that first choice. I am looking at the unbound variables and just picking the first one, basically picking a variable at random. Then what I do is, of course, I'm about to bind it, so I remove it from the unbound variable set, and I add it to the bound variable set. Then I make the variable true. I tell the variable you are true. I then take the formula and remove all the true clauses from it. Okay? So that method right there is going to search through the formula, look at each clause, and remove all the ones that are true from it. However, if it finds that one of the clauses is false, it's not going to remove anything. It's going to return false. So this call will return false if there was a false clause found, in which case the formula is not changed and we skip this whole step. Or it'll return true if there weren't any false clauses. And it also returns as this out variable the clauses that were pulled out of the formula. Okay? So at this point, if we get to this point, we know that there's still hope. We're not stuck, and hopefully the formula has shrunk because we've taken out all the true clauses. Then we just make the recursive call. We say, is that solvable? And that'll either return true if further work got us to a winning point, or return false if it didn't. If it returned true, we return true. No need to keep searching. If it returns false, we undo the removal. So we put the true clauses back into the formula. We set the variable to false, because setting it to true didn't work. So now we try setting it to false. Do the same thing. We print out the true clauses, try to solve it. If that doesn't work, we add the clauses back in and unset V, so now it's unbound, and we put it back in the unbound set and return false. So this is a very typical kind of backtracking search, where you start with a problem. At each level of recursion, you produce subproblems, simpler subproblems to solve. So where are we producing the simpler subproblems to solve? Yeah.
True clauses.
Yeah, it's right here and right here. So we prune the true clauses. Well, the way we produce a subproblem is we pick a variable and we say, okay, assume it's true, prune out the true clauses, and recurse. So the recursion is now for a simpler problem. More of the variables are bound, and the formula may be shorter. Okay? In this case, there are two subproblems at each level of recursion, because we're just picking a variable and there are only two choices for it, true or false. So at each level of recursion, we pick a variable and set it true or false. How deep can the recursion go? Yeah?
Number of clauses.
It's not the number of clauses that governs the depth of the recursion. Yeah?
Choose the number of clauses.
It's not that either. Yeah?
Number of variables.
Number of variables. Because at each level of recursion, we pick a variable and bind it. So, after we bound every variable, it's going to have to be the case that either every clause is satisfied and it's true, or some clause is false. So you can't go deeper than the number of variables. Now, if you knew in advance that there were, say, 5 variables, you could write this without recursion. How would you do it? Yeah?
You try all 2 to the 5.
Well, yeah, but you try all possible, all 2 to the 5th ways of assigning true and false to variables. How would you do that systematically without recursion? Yeah?
Could you just kind of, I guess, almost a binary sequence for each of the variables and just iterate through all the permutations?
Yeah, you generate permutations, or that's not the way, that works fine. That's not the way I was thinking of. Yeah?
If you assign each variable an index, okay, that iterated 0 to n minus 1. And so each of those corresponds to a bit in a number.
Okay.
So then you just go iterate through that number.
Yeah, so he's proposing a way to generate the permutations. What I was hoping someone would say is we could just make 5 nested loops. You have one loop that tries both possibilities for x0, another loop that deals with x1, another loop that deals with x2, x3, x4, and so on. Okay? If you had 50 variables, you could make 50 nested loops. So of course, we don't know how many variables are. That's why we have to use recursion, because we don't know how many loops to write. You can't dynamically create the loops at runtime. So what we do is we take the whole problem, we choose some way to produce simpler subproblems. And we only have to produce 2 in this case. It's enough to produce 2. And we recursively solve the subproblems. That's the structure of backtracking. Now, what determines whether backtracking is fast enough? Yeah?
You're able to quickly prune out all the bad.
Okay, he said you got to be able to quickly prune out all the bad. The important word he said was quickly. You've got to sometimes you got to think pretty hard in order to make sure that these basic operations that you're doing over and over again each level of recursion are fast. So, for example, I made sure that pruning clauses out was fast. And I made sure that it gave me the true clauses back. It gives me the clauses that are given back, so I can put them back in at the end. Now, what would be another way to do the same thing? Suppose there was no method to put clauses back into the formula. What would we have to do pruning? All right, suppose we got to this point right here, and this parameter didn't exist. All we had was a method which removed the true clauses from the formula, just modified the formula. It didn't tell you what it had removed. Yeah?
You could make a copy and just remove it from that.
Okay. So what you'd have to do is make a copy. So this is a solution that often occurs to people. You take the formula, make a copy, modify the copy. So you'd prune out the true clauses, you'd make the recursive call, and then when you're done, instead of adding the clauses back, you would just throw away the copy, and then you would make a new copy and prune it. So you have to make a copy before every recursive call, and then you could abandon the copy. What I found, I do more of this sort of thing than you might imagine, because I'm interested in puzzles, and a lot of times when I can't solve a puzzle, I write a program to solve the puzzle. And this is the sort of thing you have to do to solve a puzzle. And the copying will kill you. Copying a big thing is going to be way more expensive than making a modification to the thing and then undoing the modification after the recursive call. So that's the pattern you typically see. Before the recursive call, you modify the thing you're solving. After the recursive call, you put it back the way it was. You undo the change. Okay? And when I'm solving a problem, solving puzzles with this sort of thing, what I do is I write the program and I see if it can solve the puzzle. And a lot of times it can't. It runs out of time, or I just get impatient. And so I just kill it and I think, how can I make this faster? How can I be more clever? And I just keep trying things until it works. Until it's good enough. You can never get it. In general, you're not going to get it as fast as you might want. It just has to be fast enough. Now, to speed this up, we could start worrying about, how can we prune more efficiently? Or is there a better way to represent clauses or variables than I have done? And I wrote this a couple years ago, and I've forgotten all the reasons for why I structured the classes that represent various things as I did. But I remember I had to put a lot of thought into it. But let's not do that. Let's put some intelligence into the backtracking. Okay? So there's implementation tricks that I've been discussing. The big one being make a change, do the recursion, undo the change instead of making copies. Make sure that all these methods are as fast as you can make them. We won't go there. How do we make things, how can we apply a little intelligence? Where's the only place we could apply some intelligence? Yeah?
And which variable we choose to.
Right. Which variable you choose to commit to. All right? We're just picking one at random, basically. I've got a hash set, and I'm just taking the first thing out of the set, and who knows what that's going to be. What would be a better basis on which to make the choice? What would be a better way to choose the variable to pick on? Yeah?
Which variable appears the most?
Okay, he said which variable appears the most. That's a reasonable answer. Who can think of some other strategies besides picking the variable? Why would picking the variable that appears the most work?
Because you remove as many true clauses as possible.
Because, okay, so then you're committing in lots of places, and the more clauses you're changing, essentially, the more likely it is one will become falsified, which is really good, because that completely eliminates the recursion. Or it will become true, in which case the formula gets shorter. What's another idea? Do you have your hand up? Yeah?
So you choose whether to set true or false first, so we can do an if statement and say we choose false first.
Okay. So he said instead of setting the variable to true and then setting it to false, you can choose the order in which you examine. You could decide, you know, I think it'll work out. I think I got a really good chance of winning this game if I set the variable to false. So look at it first. Okay? We'd have to figure out some way to make that decision. Janelle, what were you going to say?
Maybe a variable that has equal proportion of true and not, like, to see if they can cancel each other out.
Okay, so maybe look for one where, you know, instead of picking one that occurs once unnegated and 10 times negated, pick one that's 5 and 5. Yeah?
Choose variables that are in the same clause. Like, choose, like, there's X, Y, Z in one clause. You would choose after X, which is Y, and Z.
Okay. Let me rephrase that. What about this strategy? You know, some of the clauses will have 3 variables, 3 unbound variables. Some of them are going to contain 2 or 1, either because that's just what they were at the beginning or because we've already bound some of the variables. What if our strategy was to pick a variable that was the only unbound variable in its clause? The only remaining variable. Basically, you have a 1 variable clause. Why might that be a win? Yeah?
You can fully evaluate that expression, so you're guaranteed to get at least one result.
Okay, so if a clause contains a single variable, let's say it's a variable x. Okay, if we set x to true, we're guaranteed at least that clause is going away. It's been satisfied. If we set x to false, the whole formula is false right then and there, and we avoid a recursion. And that is where you win. You win when you can avoid making recursive calls, because a single recursive call can lead to who knows how many other recursive calls. Now, what if there isn't a formula with only 1 variable in it? Choose one from a clause that has only 2. And if otherwise, we choose one that, you know, we choose one at random, basically. Yeah?
Curiosity, why can't we enlist the help of multi-threads? You like true on one thread, false?
Oh yeah, we could certainly. That would be the way to speed it up too. You know, we could make the program twice as fast probably just by the first level recursion, just launching 1 task for true, 1 task for false. Now the problem of doing that at every level is you eventually, you know, you're going to get more threads than quarters, as the number of subproblems doubles at each level. But yeah, we could certainly do that trick. Yeah.
Couldn't we also blend these algorithms so that once you're small enough, you just brute force the rest of it?
Yeah, I mean, you could. He suggested blending it so that you try to be clever about picking the variable for a while, but then you just brute force it at the end. Yeah.
How about memoizing it so you remember
Okay.
clauses?
So lots of things we could try. I'm just going to try one thing. So right here is where I pick the variable. Right now, I'm picking the unbound variable, just the first unbound variable, which is basically picking at random. Here, I'm going to be intelligent about it. I'm going to choose the formula. I want to choose a variable, hopefully from a clause that only contains 1 variable. If not that, from one that contains 2. Otherwise, one that contains 3. Now, the thing about making an intelligent choice is you need to do it efficiently, right? You don't want to have there's a trade-off. Maybe you can make a really smart choice if you spend a lot of time making it, but that's going to slow things down. And for all these suggestions you've made, any of them might pay off. They may all pay off. It's hard to know until you try it out. So what I have to do to pick more intelligently is I'll just change this to false. So instead of making an arbitrary pick, I'm going to make a smart pick. Okay? So 40, when I did this test case right here for 40, it took like what? 700,000? $243. I think that's astonishing. You wouldn't think it would make that much difference, but it makes a huge difference. Yeah?
So your intelligent choice was to pick a clause with the lowest number of variables?
Yeah, I find the clause with the fewest number of variables, and I pick that variable. So I'm looking for a clause with one variable ideally. When I find it, that's the variable I use. Now that variable may be unnegated, it may be negated. But the reason it pays off so much is that either, when we're going to use true for, we're going to, let's say x is a variable. We're going to make x true and then we're going to make it false. One of those choices is going to make the clause false, which makes the formula call false, which avoids the entire recursion. So now, if we manage to do this at every level, pick a variable with only, a clause with only one variable, there's no branching. It's just recurse, recurse, recurse. Either to succeed or to fail. And so with, with that, yeah.
So you're checking whether or not the variable will make the clause false by trying first true and then false. Could you like try both of those before you recurse at all, so that you try the one that made it false first?
Yeah, I mean you could do that. You could do it in either order if you have some basis, some reason for them to do it.
Yeah, just so that you can try the false one.
Yeah,
and then just
you could do that. So we can go a little higher now. So I can go up to 100 variables. But keep in mind that this isn't like making it twice as hard. It's making it 4 times harder because the number of possibilities doubles just every time I increase this thing by 1. Okay. So in that 100 variables, it goes up to 14,967 calls pretty quickly and says there's no solution. Now this will, I'm not saying this is a miracle,
Well, more.
but it's certainly better. So let's go up to 200. This probably.
Should we decrease the number of clauses too?
Yeah, I mean, we could mess with it, but.
This becomes easier and easier to solve our constrained problems.
Yeah, this is probably going to be too many for it. I'm only willing to wait for a certain amount of time. Okay, there's plenty of room to improve this, but you can certainly see that just that tiny change we made, just by spending a little bit of time at each level of recursion to pick the right variable, and that's actually can be a pretty expensive method, right? Think about the first level of recursion. It's going to search through every one of these clauses, and there's like 1,000 at the beginning. And it's not going to find a variable that's the only one in its clause at first. So it's wasting all that time at the low levels of recursion. So maybe we could do that. Try to make the intelligent choice until we're a couple levels deep.
Could you try to make more expensive intelligent choice early on, and then cheaper ones as get?
Yeah, there are all kinds of strategies you could apply. In my experience in solving these problems is you just keep trying things until it's good enough, right? You're not going to make it perfect. You've got some problem you're trying to solve, so you just keep going. Yeah. Yep, it's still running. So, any questions I can answer? Any other questions I can answer about this? Yeah.
In general, is there usually something that you'll find that's way better than the rest will dwarf it, or is it just an amalgamation of so many tweaks that makes it?
Yeah, usually it's hard to say. When I was solving the traveling salesman problem, I tried a whole succession of things, and I think my experience there was I would run it and I would pass 6 test cases. Then I would think of a way to improve it, and I would go to 7 test cases. And I think another way to improve it, and I would go to 8 test cases. So it was like a series of little improvements. And I've looked at what some of you have been doing, and I see the same pattern. You can look at history and see how over time you pass more and more test cases. Yeah.
But it's hard to see that when they have all the test cases like 2 visible test cases, like they're writing the test problems now where, like the previous one, where they have a bunch of test cases.
Yeah. Yeah. All the ones I wrote were written with the idea that we would be grading them. And so I create lots of test cases. And these ones that I didn't write, like the last one, tend to have lots of test cases packed into an official test case, which I kind of find annoying. Yeah.
Are the test cases for traveling salesmen just more difficult in terms of the time constraint?
They're just bigger.
Okay.
They start at like 3 by 3 graph, like a 3 vertex graph. They go up to like 22 or something. Yeah. So anyway, I don't think this is going to finish anytime soon. But. So, you know, I got a long way before I could compete with an industrial strength
Do you
solver.
like plot the number of clauses you got right and see if you're getting closer and closer? Or?
Yeah, I mean, there's no end to ideas that you can.
I meant for.
Oh, for that, yeah. There are other ways I can make this, change it for educational purposes. See how fast, how close we're getting. Yeah.
Is it an industrial strength? What makes the industrial strength industrial? Bigger computer or?
Well, a bigger computer, use parallelism, use more advanced ideas. Like I don't remember the talk very well, but the one I was mentioning, one thing they did was, they said occasionally they would backtrack more than one level. So they had this way of sensing that they just weren't making progress. And so they'd say, heck with this. And they would just blow away a bunch of level recursion and try a different level. Now, that's a heuristic. That's not guaranteed to win. It may be when you make that decision, you're not going to find a solution that existed. Yeah?
Would you maybe save that giant bunch that you just cut off in case you don't find a solution?
Yeah, I suppose you could, yeah.
How about linear programming? I mean, this is branching down and backtracking. Is there a way like to pull off linear programming in this, like branch and cut?
Yeah, I mean, I don't know. I'll let that run while I'm, we'll see what happens. Usually don't have the patience. So now I have, we can talk about backtracking in the abstract now. All right, what's the magic you type to go into
F5.
Wait, this isn't even showing up.
It might be the C# true in your entire processor.
Yeah.
Control C to save well, Visual Basic.
If it's threaded, it could.
Control delete.
I will. Sorry about it.
Oh.
You can, I'll post this, you can run it at home. All right.
Overnight.
Oh, yeah, we had this problem before. We just press F5, right?
Yeah, but it hasn't down, it's like it's not seeing the slideshow. So I'm going to kill, there it goes.
Look at it.
Oh, yeah. Darklight really likes me.
Yeah. Okay, let's try this. PowerPoint. Okay. All right, so here is sort of a description of iterative backtracking in the abstract. So try to connect this to what we were just talking about. So you start with a problem. That's the formula with all the clauses. And you have a set of active subproblems. And initially it's just the top level problem. While that set's not empty, you choose some subproblem from the set. Okay? Now this is iterative backtracking, not recursive backtracking. What I just showed you was recursive backtracking. In my experience, iterative backtracking doesn't work. Maybe I just do it wrong. But let me just explain the difference. So we have a set of subproblems to work on. We take that, so the thing in yellow is where you can apply some intelligence. So we choose which subproblem to work on. Initially, there's just a top-level subproblem. Then we expand it into some smaller subproblems. Now, what's that correspond to in 3-SAT, the expand step?
Oh, that's when you pick the variable.
That's when you pick the variable and produce two simpler subproblems. So you create those subproblems, and then for each subproblem, you test it and see, am I done? If so, report the answer. Am I stuck? If so, throw that subproblem away. Otherwise, the subproblem is interesting, you add it to the set. And you just loop on that until you either use up all the subproblems, run out of subproblems, or you find a solution. So, what makes this, there's no recursion because we take the subproblems and add them to the set. What happens to that set over time? It gets bigger and bigger and bigger. And that's the problem I've always had with iterative backtracking, is the set of active subproblems gets too big. So what you can imagine doing is using a priority queue to contain the subproblems. And what would be the, how would you, what subproblems would make it to the top of the priority queue? How would you decide that? Yeah?
Maybe do the smallest problem sizes first?
Maybe the smallest problem sizes first, who knows? You would have some way of comparing subproblems to decide which was the best candidate to use next. So that would be sort of a way of approaching this bailing out and trying something else. You'd sort of lose faith in the subproblems you're working on and something else bubbles to the top of the priority queue. But again, in my experience, the queue just gets too big.
How do you build your subproblems back into the original problem? Like, we keep breaking it down, but how do you build
Well, okay, so what happens in my 3-set example is, as I go down the recursion, I'm setting variables to true, to false, to false, to false, to true. When I hit the bottom and I've succeeded, all those variables are set. Okay? And all those variables are sitting in the bound variable set. At that point, I just return out of the recursions, and then I can look in the bound variable set and pick out how each variable is set. So it remembers its solution that way. Okay? So these are all places where you can apply intelligence, these yellow things. So this is what iterative backtracking would look like. So there's a 3-sat example. That's our initial formula, our initial subproblem, our initial problem. And we pick a variable, we generate some subproblems. We can pick W. I guess W is one of only 2 variables in its clauses, in some of its clauses. So those are our 2 subproblems. Now, we've got 2 subproblems in our queue. We've got to pick one of them. So maybe we pick that one, and we decide to expand on X. Now we've got 3 subproblems in our queue. And we pick one to, we pick that one, let's say. All right? So we simplify if Z is false, we simplify if Z is true. Now, at this point, we're stuck. Empty parenthesis means we have, we failed. That's false. So we would have, the way I wrote the algorithm on the other slide, we would have tested these and seen that we're stuck and basically discard both of these subproblems. So those subproblems aren't really in the queue. So we pick, there are only 2 remaining ones in the queue, so we try that and that. That one gets discarded because we're stuck. Now we pick that. Both of those were stuck. Now we've got one other subproblem. Oh, I guess I'm stuck on all of them because they're all empty. Okay? So we only considered 6 possible assignments this way. Right? So that's intelligent iterative backtracking. And it worked here, but lots of variables, this queue can become huge. Okay? Any questions I could answer about that? It's a lot of the same considerations go into making this work that go into the recursive version. Yeah?
So if there's no solution, then even the recursive version would try all solutions, but try all possibilities, right?
Well, okay, there was no solution, and we did not try all the possible truth values. Recursive version won't either necessarily. Just depends. If you're really unlucky and you pick the wrong variables to expand, you can end up looking at all the possibilities. Right, this is recursive backtracking, which I just showed you on the slide. This is the base case. If we have won, return the solution. If we have failed, return null. I was returning true and false, and the solution was stored in a global variable. Otherwise, we expand each subproblem and search it. So you're not able to, in the iterative version, you've essentially got a conception, you've got a tree, and you're looking at, you can pick your subproblem from anywhere on the fringe of the tree. This is recursive, so you're always concentrating on a current node. Now, we decide how to expand the subproblem, so we can be clever there. We can decide the order in which we consider the expanded subproblems. We can be clever about these tests. And so this is what that looks like. We try that, we say, okay, let's take W and make a recursive call. Then we say, okay, what if X is false? We make a recursive call. Now we say, what if Y is false? We get there. We try what if Z is true? We get stuck. All right? Then we back up to here. Try another way. We got stuck. We back up to there. We get stuck. We back up to there. We get stuck. So we go over here, and so on. same sort of thing is going to happen. So in the iterative approach, the amount of space you need is proportional to the fringe of the tree, the leaves of the tree. In the recursive approach, it's the depth of the tree. And clearly, the depth of the tree is going to be the number of variables at most. And if you're just talking about a couple hundred variables, that's fine. The fringe could be, at worst case, 2 to that. That's why I have my doubts about iterative. Yeah?
Are there any opportunities to memorize this?
I'm sure there are opportunities to memorize it. For example, the traveling salesman problem, when you solve it, there is a dynamic programming algorithm for TSP. But all it does is it turns what would be an n factorial algorithm with trying all the possibilities into an algorithm that's 2 to the n times n squared. So it's better asymptotically, but it's not like you've come up with a polynomial time algorithm. Now, you may notice, if you look at the leaderboard on the TSP problem, the top solution is 0.02 seconds, which is 40 times faster than the second place solution.
Who is it, Joe?
Yeah.
It's this guy named Sam that I know. But I happened to see him yesterday, and I asked him about his solution. He said he tried the CARP algorithm, the n squared 2 to the n, and it took about a second and a half. And so he abandoned that, and his solution is just, it's just branch and bound. And he was trying to explain in the car to me what all his tricks were, and he thought about it pretty deeply. So.
Is he going to release his code?
Yeah, he's not going to release his code or his tricks. But. Okay? So, anyway, that's backtrack. It's a really good pattern to know. And the basic pattern is, you got a problem, you create subproblems, and you recursively solve them. And what often makes all the difference is, you don't want to make copies of the problems. You want to take the problem, modify it, make the recursive call. When it returns, unmodify the problem, and then try the other direction, rather than making copies. So setting things up so you can efficiently do and undo changes is a big win. And that's something that works in the recursive pattern, but won't work in the iterative pattern. So that's another reason to do a recursive. Okay, any other questions? Okay, we will take a short break, and then we'll look at branch and bound and see how it differs. All right, let's get started again. Okay, so the optimization problem version, equivalent of backtracking, is branch and bound. So here we got to, if you take out the bound part, just have the branch. It's like the recursive backtracking, except when you find a solution, you still got to back out and try the other way. You're just looking for the best answer. So I couldn't think of a better example to illustrate this than traveling salesman problem. So here, you're welcome to, I haven't posted it yet, but I will. Here's a starting point for the caddis problem. Okay? Part of my trying to make things easier here in the last week. So let me explain how my TSP algorithm works. So again, I'm using statics for a lot of the parameters, not all of them as you see. The things that don't change, I just want to avoid passing around. So I have the number of vertices, V. I have the graph. Now notice I've used an adjacency matrix for this graph, not an adjacency list. Why is it better to use a matrix? Yeah?
Because we know that in the traveling salesman problem, it's a complete graph.
Well,
so every single step.
yes. At least the version of the TSP that on caddis, it's a complete graph. And so it's definitely as dense as it gets. So you want to use this just to speed up, speed up lookup. So now the other thing, this is key in branch and bound. You're going to have the best answer you have found so far. So initially it's infinite, effectively infinite. And what we're going to do as our algorithm runs, as we find a better solution, we'll replace that, and gradually that will come down. And when the method is returned back to where it's called from, best so far will contain the answer. And then this tells me as I grow the path, I'm growing the path and trying to go back to where I started from. That set will contain the indices that we visited already, the vertices we visited already. This just reads in the graph, so I'll skip that code. First thing I do, I'm going to always start from vertex 0. It doesn't matter where you start. And you certainly don't want to, let's say you start at 0 and don't find a solution. You don't want to try starting at 1. That's not going to work. I mean, you're not going to find a solution. It doesn't matter where you start. So we'll start at vertex 0, so I add it to the visited set because we've already been there. Then I call TSP solve, and we'll see what those parameters are. And when we're done, I print out best so far. Yeah?
So there's a diagonal that runs from the top left to the top right. Are you never going to make a move down?
Yeah, the numbers on the diagonal don't matter.
So
You would never use them.
It's like a potential optimization that you don't have to like...
Well, it might, that's really small. Because you put them in the graph, you never look at them. So there's really no overhead except creating the graph in the first place. All right, so here's my method. So what it takes is the current vertex. So conceptually, we're building a path. The current vertex is the last vertex on the path so far. Current total is the total weight of that path from 0 to the current vertex. And current length is the number of edges. Or I don't remember if it's the number of edges or if it's the number of vertices. It's the number of edges. Number of edges on the path. So initially, the current vertex is 0, the current total is 0 because we have no edges, and the current length is 0 because we have no edges. That's why we pass 3 zeros to TSP solve. Okay? Just like with the backtracking, there's a base case. If the current length is V minus 1, the full path will have V edges. Right? So if we have V minus 1 edges, then all that's left is to go from the current vertex back to 0 to close the loop. And so what I do is, okay, the current total plus the cost of getting from the current vertex to 0 is going to be the total cost of the cycle. And so we try to update best so far. We take the min of best so far in this new thing we just found. Okay, that's the base case. Then when we return from the base case, we'll try some other, we'll make some other choice somewhere else. So this is where the recursion happens. So what we do is, we're at some vertex, and we've got to try going to other vertices. We've got to try all possibilities. So I iterate through the vertex numbers, 0 up to V. If I haven't yet been to that vertex, this is what the visit array is for. If we haven't been to the vertex, then we consider it. If we have already been to that vertex, we don't consider it. So we're just concerned about visited vertices here, unvisited vertices. And then what we do is we add it to the visited. After the recursion, we remove it from the visited. So there's that theme again of making a change and then undoing the change. We're not making copies. Vertex becomes our current vertex, the last one on the path. So conceptually, we're adding the edge from the old current vertex to this vertex that we're getting from the loop. So that's our new current vertex. Our new current total is the old current total plus the cost of that edge that we just conceptually added. We're not recording the path anywhere because we don't need it. And the current length has gone up by 1. And that's all there is to it. That's the basic. This will find, if you wait long enough, it'll solve any TSP graph. It certainly won't pass all the test cases in CAS. But it's a good starting point. Now, before we talk about making this more intelligent, in other words, we're not using branch and bound, right? We're just using branch. There's no bounding being done. Can you think of any attacks you could make on this, any ideas you could have to make it, just to make the base code faster? Yeah?
Well, we're already keeping track of the best so far. So if we know our path at any point is bigger than best so far, we can abandon
Well, that's the bound part.
Okay.
So the independent of the bound part, yeah.
So, why not just iterate through the visited thing instead of having the for loop?
Okay, well, what we'd want to, all right, so that's the idea. This loop can be fairly expensive, right? If almost every vertex has been visited, we're doing this loop, and since most of the vertices are visited, the iteration is kind of a waste. So an idea might be, what if you had an unvisited set? Instead of iterating through all vertices, you just iterated through the set. Okay? Now I didn't implement that because I was thinking, okay, so you're iterating through the set. What are you going to do when you find it? So you pull the first element out of the set. What do you do?
Did your son do that?
I don't know. Okay, so just imagine if we replace this with something like for int vertex in unvisited. So imagine we had an unvisited set, and that would have to be for each. So what if we had our loop? Okay? So then we would get rid of this right here. Right? We just iterate through the unvisited vertices. What's the problem? Yeah?
You're modifying unvisited.
Right, because what we have to do is, instead of adding visited, we would remove from unvisited, and then we'd add it back here. But now you've got a concurrent, you get an exception if you modify the set you're iterating over. So I just didn't feel like working out the details. There may be some way around it that doesn't, there's certainly a way around it if you just make a copy of the set. But I want to avoid copying the set. But it's something to think about. Okay? That would be the main way, if I were trying to think of a way to make the base code faster, that I would do. Because there's not, the rest of it's pretty stripped down. Now, notice that we have to explicitly add and remove. Add and remove. But why don't we have to do and undo the current total, or the current length? Yeah.
Because they're just passed by value to the next.
Yeah, they're just passed by value, right? So it's not like we're reassigning current length. We're just passing current length plus 1. Current length doesn't change in this stack frame. Okay? And one thing just occurred to me is you could do something like compute current length plus 1 and store it in a temp. And then just pass the temp each time and avoid doing that addition. But I bet the compiler will, if you run in release mode. Of course, you don't get to choose that in CAS, do you? I don't know. So anyway, those are things you can try. Now, so let's copy this and go try it out. Problem here, right? Utah.tsp, that's not Java.
Passing all tests.
just passed all tests, you'd be happy.
It's gonna take a while because. That's like only
Have points for copy.
Okay. So it passes 5 of the, anyway. No one needs to get a 0.
Yeah.
Okay. So, let's go see if we can get the grade even higher. So, what we want to do now is bounding. Yeah?
Would you recommend using a language faster than C# for this problem, or not?
Yeah, certainly, if your program is just too slow by a factor of 2, which is hard to know, but then going from Java to C++ will definitely get you over the hump. It's not clear to me that going from C# to C++ will work. Anthony got over the hump by going from Python 3 to Python 2. Yeah.
I converted my solution from C# to C++ but
By a factor of 3? All right, now take back what I said. Yeah?
C++ doesn't have concurrent modification checking on it, so yeah, be careful. That's true.
Say that again?
He said C++, it's like a lot of other things. C++, he said, doesn't have the concurrent modification check. So,
multiple threads don't help on caddis.
so, what's that?
Multi-threading doesn't help you on caddis.
Okay, yeah, he wasn't talking about multi-thread. This was changing the thing you're iterating in the loop. And instead of giving you an exception, it just goes haywire. Yeah. I have noticed over the semester that people in C++ will have these problems, and I'll think, wow, why didn't I ever hear about this before? And the reason is, in every other language, it was an exception that got generated, and people knew something was going wrong. C++, you know, it just goes crazy. So it was definitely a trade-off here. Okay, the easiest thing in branch and bound, you really don't have to know anything about the problem, would be what? What would be the simplest bound to make? I think someone already said. What's the simplest improvement?
No, like the remaining.
Well, even simpler than that.
Oh, it's less than, it's greater than this.
Yeah.
If you already have a best so far, check if it's already greater than that.
Right. So when I come in at the top here, why don't I just say if current total is greater than or equal to best so far, there is no point in continuing, right?
Can you do that before you call it?
I could do it before I called it, but
And then use the new current total?
yeah, but I don't know. It doesn't make a huge amount of difference, and this is, you know, anyway, you're certainly welcome to make the change. See if you can improve it. So that's the basic branch and bound idea. If you already, you know, if the best so far is 100 and you're not done yet and you're at 101 or even 100, there is no point in pushing forward. There are no negative edges. If there were negative edges, it would be a different matter. So just give up. I mean, give up on this branch, try differently. So let's see. So what did I do before? 5?
Yes.
Am I doing this wrong that I have to keep resetting this every time?
You have to file.
Or I keep having to pick the language?
You don't have to, you drag and drop.
It automatically takes
Oh, okay. Anyway,
What was the answer? It automatically what?
if you drag and drop, it automatically detects the language, I guess, from the file extension or something. All right, so let's see just how that simple change changes things. Okay, so we're already at 6, and I think that's as far as we're going to get.
So it's about 15. 15. 12. Well, it goes 13, 15, 17.
Okay, but just that simple change got us up one level. Okay, so that's half, right?
So calculate like a best possible from where you're at.
Okay, so let's try, well, I'll try one more because I don't want to just stand up here and do the problem for you. Okay? So we know that every edge is of weight at least 1, right? So to current total, we know we're going to, how many edges are left? Well, there's current length and there's going to be V edges. Currently, there are current length edges, so we'll just add to this estimate V minus current length. Okay, so for each edge that we haven't put in, that we haven't considered yet, there remain to be V minus current edges to add. Each of them is going to be at least 1. So let's let that be the amount. I'll just stick to my old ways here.
Wait, you took IT.
I'm sure you folks are all experts at this by now.
So once we get close, we just like randomly subtract number and.
No, that's all right. So let's see. Let's see. Yeah, I don't think it's going to be much difference. Okay. No, that's a time limit exceeded. Okay. So that wasn't enough. What's another thing you could consider there? Instead of adding 1, what'd be? Yeah?
I guess you could check what the minimum weight in the graph is, so like
Right.
it's not guaranteed to be 1.
If you knew what the minimum edge, suppose you knew the minimum edge in the graph, the weight of the minimum edge in the graph, which you could calculate once ahead of time, right? Then we could just say V minus current length times min edge weight. Okay? Which can't be, there can't be an edge less than that. What the heck? Let's try that. So let's see what we got to do. I got to have a min edge weight. And then down here, each time I read min edge weight equals math.min of min edge weight and this thing here. Now, this isn't the world's most efficient way to do it, but I'm just in a hurry here. So.
You got to set min edge weight though, because it starts off as 0.
Thank you. Okay, see what I did there?
Yeah, I don't think you want to.
You're on one.
Got to set it to max.
It's good to have you all here.
Or you just set it to 500. It'll never be above 500.
Okay, that look good now? Of course, we can make this faster by just doing the parse once, but maybe the compiler will help us out.
Or you said you wouldn't give us any edges greater than 500, right?
Okay, yeah. Well, anyway, good enough. All right, what's the fast way to do this?
Control C, and then edit.
Whoops.
Oh, nice.
Copy it,
And then click the ID number in your try.
right here.
Yep. And it should be
Recent.
it's a
Edit.
recent.
Is it different?
It's different because
Just hit where it says problem.
Oh, you have all the tools that you said.
Salesman.
Okay, I could have had it done already. It's hard to listen to everyone making suggestions sometimes. This is the last one. Last one. All right. I have no idea. I didn't try this last night, so I don't know what it is. It'll be embarrassing. It won't be embarrassing, but it'll be sad if it solves it all. How many of you have been working on it and haven't gotten that far? So anyway, I don't want this to be a frustrating experience, So you don't have to worry about. I mean, this gives you the starting point, and it's easy, as you have seen here, to experiment with doing better and better bounds. And just keep in mind that you can probably think of some really good ways, but if it's too expensive to calculate the bound, then that may not pay off. And so it often pay off. Imagine if we had to calculate the minimum edge each time we did the test instead of doing it in advance. So anything you can pre-calculate, it's going to work well. And it's going to take some ingenuity to get all the way to the end, but So,
Wow. That's 8.
all right. So I'll put this online, but I'll probably forget. So I'm sure someone will remind me. Okay, now let's go back to PowerPoint. And let's look at.
It's gonna be normal scoring on this last one.
On this last
Grading.
one?
It's gonna be normal
Yeah,
grading.
the scoring on this last one is, it's not sort of, it's, if you get X% of the test cases, you get X% of the points. So getting close gets you close to a perfect score, unlike previous CAS problems. Okay. So, this is branch and bound again. This is like the sort of the general case of branch and bound. And again, this is iterative version. We just did the recursive version. But essentially, you start with a problem like before with backtracking. You let S be the set of active subproblems. Best so far is infinite. Now, if you're doing, sometimes you're doing a maximization problem, so there it would be negative infinity. While the set is empty, not empty, you choose some subproblem from the set. So again, that's a place you can be clever if you're doing it iteratively. If you're doing it recursively, there is a little bit of room for this choice. So what would be, we'll talk about when we get to the recursive case. But here you've got all this big set, you choose the one you want to work on, whichever one you think is, you can figure out is most likely to pay off. Well, why does it matter which you choose first, since you've got to try all the possibilities anyway? Or, well, why does it matter which you choose first? Yeah?
If you can set best so far well early, you can cut a lot of stuff out.
Right. If you lock on to a solution, so in this one, since the graph is complete, it's never going to fail and have to back up. It's always going to reach, unless you have the bound set, it's always going to reach a solution. So if you could find the best solution first, then your branch and bound starts working really well. It starts pruning. So it's a big payoff to get a low best case in there first.
So use heuristic.
Well, so he asked about heuristics. The danger with heuristics are basically ways of making choices that may or may not pay off. And the problem with a pure heuristic is, a heuristic would be, I'm not even going to try this subproblem because it looks like it's not going to work out. It's not going to improve. But if you're wrong, you've missed the solution. So for this one, you don't want to use heuristics because you've got to get the right answer. Okay, so you choose which one you want to work on from the fringe of the tree, except it'll be in a priority queue. You expand into smaller subproblems. For each one, if it's a complete solution, you update best so far. If it's not a complete solution, you do the bound part. You make some estimate, and if it can possibly pay off, meaning it's still less than best so far, you keep it. Otherwise, you throw it away. And when you're all done, you return best so far. So the yellow things here are places you can apply some intelligence. Recursive branch and bound. Let me see where I'm headed. Recursive branch and bound. You start with the problem, best so far, you call optimize. If it's a complete solution, you're done. That's the base case. Well, you're not done. You're basically at the end of the recursion. So when you got a complete solution, so you've closed the loop, update best so far. Otherwise, you apply the branch and bound thing. So if it makes sense to go forward, you generate the subproblems and systematically deal with each one. Okay? So that is clearly a place where you apply intelligence. What would this correspond to? In TSP case, you've got some subproblem, which is a partial path, partial cycle. Yeah.
That's the next vertex you want to go to that you think will be part of the Hamiltonian cycle.
So right here, the subproblems you generate are going to be an edge to some unvisited vertex. So there might be 5 unvisited vertices. So you consider extending the path to all 5. So you can apply some intelligence here by choosing which order you consider those vertices, maybe. You've got some reason to think going to vertex 4 is likely to lead to a better solution than going to vertex 5. You want to do that first.
So short the edges and pick them.
I mean, Hard to say exactly what it worked. Now, we did this example last time. So when you read, if you read the book, in the chapter on this, it says one way you can improve, the way you can put a bound on traveling salesman problem is, okay, so you know the vertices that you have traversed so far. You know that you've got to hook all the unvisited vertices together in some fashion in the future. And you've got to hook the visited vertices to the unvisited vertices. So essentially it was, what we described was using, at every level of recursion, computing a minimum spanning tree for the remaining unvisited vertices, which would give you a lower bound on the cost of hooking all those up. And so the bound would be the cost of the minimum spanning tree, the current length of all the edges that you've already used, and then the two lightest edges that lead from the visited vertices to the unvisited ones. Okay? And that's great in the abstract. I tried it out once. Failed miserably. Didn't speed things up, it slowed things down. What was the problem? Yeah.
You have to compute the minimum spanning tree at every single level.
Right, minimum spanning tree algorithm at every level of recursion. It was just too expensive. The cost of computing the bound was too high. And so even though the book talks about it, I don't recommend that as an approach. You've got to find a cheaper way to set the bound. Now, if you really want to go full out, you can try, instead of, what you want is, you compute a minimum spanning tree. So the first time in the recursion, at the first level of recursion, you're computing a minimum spanning tree for the entire graph except for the starting vertex. Then you pick an edge. You want an algorithm that will take the minimum spanning tree you just computed and compute a new one from that. That would be a solution for all the vertices except the one you just went to. So you need something that will let you take a minimum spanning tree and shrink it, shrink it, shrink it, shrink it as a set of vertices shrinks. An incremental algorithm. So that rather than computing it from scratch each time, you base the new minimum spanning tree on the old one. And there are algorithms for that. A little hard to dig up online. But I think your time is better spent trying to find better ways to set the bound. But anyway, we went through this animation, but it illustrated branch and bound. And you can see that we don't generate the whole tree, things get cut off. So then the end, I'm not interested in the details right here. So that's how we solved the problem by, all these places were places where we realized that we were higher than the best solution found so far. And you could, rather than having a tree with n factorial leaf nodes, we have much more manageable number. There's the end. Okay? And other ideas for lower bound we have, there's some you can look at. See if that's all of them. Okay? So there are some things you can think about. We've talked about some things you can think about. Kick ideas around. Let's see what you come up with. It'd be nice if everyone could find a way to the end of this. Okay? Any last questions? Yeah? Yes, we have class Tuesday. There are a few more things I want to talk about in terms of coping with NP completeness. And so we'll do that at the beginning, and then we'll do a review. And like I said, Stefan will be scheduling another session to go over the sample final.
Everybody go fill out the poll.
Yeah, fill out that poll because we got to get a room reserved and all that.
You can vote for as many times as you want.
I doubt that's even possible.
Well, in the poll.
Yeah, vote early, vote. Okay. See you on Tuesday.